The latest attempt to rattle the foundations of cosmology appeared as a smattering of dots pulled upward into a cosmic sneer. The arc of distant galaxies, which Alexia Lopez presented at the American Astronomical Society's meeting in June, sprawls so far across the sky that it would take 20 full moons to hide it. Spanning an estimated 3.3 billion light-years of space, the smile-shaped structure joined a controversial club, Unexpectedly Big Things. It's so big that it's hard to explain with our current beliefs, Lopez, one of the astrophysicists at the University of Central Lancashire who identified the galaxy chain, said during the presentation. Lopez's giant arc seemed to clash with an idea that has guided astronomy for centuries, that the universe has no conspicuous features. From a zoomed-out perspective, no matter where you are or which way you look, you should see roughly the same number of galaxies pinwheeling around. This assumption, enshrined as the cosmological principle, has let researchers draw sweeping conclusions about the whole universe based only on what we see from our corner of it. If that turns out to be wrong, then we have to redo many of our measurements or reinterpret many of our measurements, said Ruth Durer, a cosmologist at the University of Geneva. As a load-bearing strut of modern cosmology, the cosmological principle has increasingly become a target. Some challengers, like Lopez and her colleagues, are astrophysicists puzzled by striking celestial conglomerations. Others are maverick cosmologists unsettled by the consensus view that most of the stuff in the cosmos hides from our instruments in the form of dark matter and dark energy. They wonder whether theorists may have conjured phantasms to patch up an overly simplistic theory of cosmology. Most everyone agrees that the cosmological principle is worth scrutinizing. So far, though, each new claim of a too big structure or other anomaly has failed to make a dent. We are trying to poke as many holes as we can, said Sheshadri Nadithar, a cosmologist at University College London, while being very skeptical of someone else saying they've poked a hole. From Copernicus to Einstein. The cosmological principle grew out of the Copernican principle, Nicolaus Copernicus' 1543 realization that Earth is not the fixed center of creation. His insight that Earth orbits the Sun rather than the other way around set off a series of humbling shifts in perspective. Astronomers proved in the 1800s that the Sun is just a normal star. The following century, they spotted countless galaxies beyond our own. We're not special, said Andrew Howell, a cosmologist at Las Cumbres Observatory and the University of California, Santa Barbara. The universe keeps telling us that. Not only is Earth not special, but nothing anywhere is special. Over the past century, astronomical surveys solidified what's become known as the cosmological principle in two ways. As powerful telescopes peered deeper into the darkness, they saw more distant galaxies appearing in similar numbers. This suggests that the cosmos is homogeneous, with matter sprinkled smoothly throughout. Think of the expanding universe as a rising fruitcake with galaxies evenly spread like fruit pieces, each one flying away from its neighbors as the batter between them expands. Moreover, telescopes pointed in different directions have all seen similar scenes. Matter is evenly distributed along every line of sight, indicating that the universe is isotropic. The cosmos's homogeneity and isotropy make it simple enough to analyze. Theorists reconstruct the cosmos's past and predict its future using a standard theoretical model based largely on general relativity, Albert Einstein's theory of gravity. Einstein's theory describes the interplay between matter and space-time, the bendy fabric of the universe. But Einstein's treatment involves 10 interlinked equations and 20 variables, a system of equations that is generally too complicated to solve. Cosmologists lean on the cosmological principle to restrict their focus to a universe acting as a smooth and symmetric fluid. By ignoring bumps of matter like galaxies and requiring the universe to expand in the same way along all three axes, the cosmological principle deletes parts of the equations and links some of the variables, dramatically simplifying the system of equations. Theorists can then predict the velocity and acceleration of the cosmos's expansion with just two equations, the Friedmann equations, derived from Einstein's by Alexander Friedmann, a Russian cosmologist, in 1922. It's a bit like computing the volume of the Earth. You could fret over every mountain and ravine, or you could assume the planet is a sphere and call it a day. As astronomers map the universe more precisely, however, a few researchers have started to wonder whether the field has pushed the cosmological principle too far. Earth isn't a sphere, after all, it bulges at the equator. In the same way, large structures or lopsided features could undermine conclusions about the universe's age, behavior and composition. Thomas Buchert, a cosmologist at Claude Bernard University of Lyon 1 in France, is among those who have become convinced that it's time to move beyond Friedman's monotone universe. "It's strange it's still alive, this standard model," he said. "Galaxies everywhere." The giant arc and other giant structures strike at the first pillar of the cosmological principle, homogeneity. The universe is clearly not homogeneous on the human scale. Teleport a person 1 light-year from here and you'll ruin their day. But drop the Hubble Space Telescope halfway across the universe, and it will return familiar-looking galaxy-filled images. In this way, the cosmological principle treats the cosmos like the air in an inflating balloon. Up close, molecules mingle in complicated ways. But from far away, a bland gas expands with bulk properties like pressure and temperature changing steadily. Galaxy surveys have found that any patch of space larger than hundreds of millions of light-years across includes roughly the same amount of matter. So structures like the giant arc, which spans billions of light-years, are as unexpected as a thick clot of air in an otherwise ordinary balloon. One of the first of these structures was identified in 2013, a putative grouping of brilliant galaxy cores known as quasars distributed across 4 billion light-years that, its discoverers wrote, challenges the assumption of the cosmological principle. Few others were convinced. Nadather, the UCL cosmologist, set out to see if randomness alone could create the illusion of megastructures. He simulated digital universes that had galaxies scattered completely haphazardly. Nevertheless, when he set a cluster hunting program loose on the smooth simulations, it picked out patterns as large as the quasar group purely by chance. Simulated standard model universes, in which gravity has drawn galaxies together into groups, would contain groupings of galaxies that were grander still. Nadather's work suggested that the cosmological principle has plenty of room for the quasar group, the giant arc and others of their ilk. Huge structures will be rare, he said, but the standard model doesn't say the probability is zero at any scale. A more convincing observation of inhomogeneity, according to Nadather, would be the discovery that matter maintains some lumpiness as you look at larger and larger scales. But studies to date have consistently found that as you zoom out, the universe gets ever smoother. Durer and other cosmologists agree that seemingly impossible structures can probably be explained by humdrum statistics. If you make many, many observations, you will have some of them which are statistically not very probable, she said. I'm not very much worried about those. Directionless universe. Even if the universe is homogeneous, it could still single out one direction for something special, an anisotropy. In such a cosmos, great streams of matter might flow in that direction like a breeze. A few cosmologists think this might be happening. Strong evidence against any sort of cosmic flow comes from the afterglow of the Big Bang. Astronomers have determined that this cosmic microwave background, CMB, has an essentially identical average temperature of 2.725 degrees above absolute zero in every direction. But to calculate that temperature, researchers correct for a slight imbalance. The CMB looks a fraction of a degree warmer toward the constellation Aquarius, and a fraction of a degree cooler in the opposite direction.